Hello viewers, in this video I will discuss about the applications of Gauss law. So in this application we will see one of the applications, that is we are going to find the electric field due to a infinitely long uniformly charged straight wire. So we are going to find what is the value of electric field due to this infinitely long uniformly charged straight wire. So now I will draw a small portions of a infinitely long. Okay, in which charges are distributed uniformly. Okay, so now we're going to find the electric field due to this charge arrangement at a point P here, which is a distance R from this. So at a point, okay. So to find the value of the electric field at this point P for this charge arrangement, what is the procedure followed? Why we are going for Gauss law? We will see each and every in detail. Okay, so we have seen a formula for electric field like this. E is equal to 4q by 4 pi epsilon r square. Whether we could use this formula to find the electric field at this point P? No, because this is the formula to find the electric field due to a point charge. But here we don't have points, we have many charges arranged together, which are varying from various distance. See, the value of r varies for a different location of the charges. Okay, so this formula could not be used directly. Okay, so whether we could use the discrete system of charges arrangement formula? No, yeah, because we see that the charges are not arranged in discrete manner. They are continuously packed like this. A continuous charge arrangement is seen here. Okay, so we could not use that formula also. So here we see that it follows a continuous charge distribution. Okay, a line charge distribution. Okay, so first we will apply the continuous charge arrangement. We will use that procedures to find the electric field at this point P. Okay, so now I am going to take this as the boundary. Okay, this is not a boundary for this infinite long. Let us assume this as a boundary. Okay, so from this charge we see that the electric field, that electric field due to a point charge will be pointing out in radially outward direction for a positive charge. Okay, so one particular direction will be passing through this particular point P. See, it will be passing through this particular point P. Another one, see that, so this from this end will be pointing in this direction. Okay, so we see that the resultant electric field, we see that this two components will be having resultant electric field. This one will be having resultant electric field in this direction and also in this direction. This component will be having resultant electric field in this direction and also in this direction. So it will have components, see, but the resultant electric field will be only in this particular directions, because these components will get cancelled out because they are equal and opposite. So this get cancelled out. So this will have component in this particular direction, this will have component in this particular direction. So the resultant electric field will be in this particular direction. So whatever may be the pairs, see, whatever may be the pairs, you see that the resultant will be only pointing in this direction, that is, it is in radial direction to this charge element. It is in radial direction to this particular charge element, whatever may be the pairs. See, whatever may be the pairs, okay, that will be the direction of the electric field. Okay, so whether we could prefer this method? No, this is also not at all possible, because if we have go long, if we are increasing the value of the length L, see that the electric field will not depend on the position of this particular point P. Will not depend on the position of this point P. As the length increases, we see that it is very complicated. It becomes very complicated by using this method. Okay. So then how we are going to find the value of electric field? For this, we are getting the help of the Gauss law. We are using the conditions given by Gauss law to find the electric field at this point P in a very easier manner. Okay. So now we will see what is the procedure involved by using your Gauss law. Okay, we came back to the initial position. So to use Gauss law, first we have to prefer a Gaussian surface. Okay, so in a Gaussian surface, we have to see that the electric field should be uniform. Okay, So we have already seen that by connecting with the continuous charge distribution, we have already seen that the electric field was always pointing in this direction, radial direction. Okay. So by considering such arrangements, we can prefer a cylindrical Gaussian surface. See that? A cylindrical Gaussian surface. While choosing a cylindrical Gaussian surface, here we can see that the electric field will be uniform. See, when we choose a cylindrical Gaussian surface, we can see that the electric field can be uniform in this particular direction. By pointing in the particular direction towards all the points, we can see that the electric field could be uniform. So it is better to choose a cylindrical Gaussian surface, because while choosing cylindrical Gaussian surface, whatever I said, electric field and also the theta will be also same in all the points. So now I'm going to choose a cylindrical Gaussian surface. Okay, now I'm going to take same similar part here also. Okay, so I'm going to close this with the cylindrical part. More or less I think similar. Okay, so I have chosen a cylindrical Gaussian surface. So why we are choosing this Gaussian cylindrical surface, we have seen the reason. So why other than this? So what happens when you choose other surfaces, that is other than cylindrical surface? So see, so if I choose a spherical surfaces for this kind of charge arrangement, if I choose a spherical surface, see, if I choose a spherical surface for this particular charge arrangement, we see that the electric field will not be same at all the points. See, because electric field depends on R. Electric field depends on R. We see that R varies at the different points when I choose a spherical surface for this particular charge arrangement. So choosing cylindrical Gaussian surface for this particular charge arrangement is more relevant, because only choosing cylindrical surface we can see that the electric field is same at all the points. Okay, so we have chosen the Gaussian surface. Now we have to go for the formula involved in Gauss law. Okay, first we have to find the value of the electric flux. So in case of this, we see that the electric field will be moving in this direction only, whatever may be the surface. So electric field is pointed out in this particular direction. Okay. Okay. Here we see that let us take this as a surface 1, this is 2, and this as 3. Fine. So we are going to find the electric flux. So electric flux total will be equal to the electric flux due to this surface 1, electric flux due to 2 plus electric flux due to 3. So we have to calculate the electric flux separately. So electric flux 1. So it includes closed integral of E dA and cos theta. So we have to find the theta value. So see here, let us consider small area element here, dA, and we see that the area vector will be pointing in the outward direction. So electric field is moving in this direction and this is pointing in the outward direction. So the angle between this is 90 degree. So here we have closed integral of E dA cos 90 degree. Okay. Similarly, next phi 2, it will be closed integral of, here also it is E dA. Here also when we take a small area element dA, it is also pointing in outward direction. We see that the electric field and the area vector are both in perpendicular direction. So the angle between them is 90 degree here also. So we have E dA cos theta, which is equal to closed integral of E dA cos 90 degree. Okay. So now we will move on to the third area. In this we see that when we choose an area element, we see that the area vector will be pointing in this direction and the electric field is in this direction. So both are parallel and the angle between them is also theta is equal to 0 degree. So closed integral of E dA cos theta. Here it is closed integral of E dA cos 0 degree. Okay, so here we are getting a value. So closed integral of E dA. because cos 0 is 1. So these value gets cancelled because cos 90 becomes 0. Okay, fine. So now, after finding this value, we are getting the electric flux phi E totally as closed integral of E dA. Fine? Okay. So now, here we see that this particular charge element has a value of lambda, that this is a linear charge density of this particular charge arrangement. Linear charge density. And this lambda is equal to the charge per unit length. Charge per unit length. So by considering this as the length of the cylinder, L. So lambda is the charge per unit length. Fine. So you know that from Gauss law, the electric flux value is equal to the charge enclosed by epsilon naught. Okay. So we have found this as closed integral of E dA is equal to Q by epsilon naught. So here it is electric fluid is constant. Okay. So closed integral of dA is equal to Q by epsilon naught. Here the value is, see this particular area, we take it as 2 pi RL. This surface area only, because these area elements get cancelled. So E into 2 pi RL, which is equal. See, we know that the charge element here Q, which is nothing but is equal to lambda L. It is lambda L by epsilon naught. Okay, so L gets cancelled. So here E 2 pi R is equal to Q by epsilon naught, in which E is equal to, lambda. E is equal to lambda by 2 pi R into epsilon naught. Okay, so this is the formula for the electric field due to an infinitely long charged, uniformly charged wire. See that the value of electric field depends on R. So if the R remains constant for whatever may be the length of the wire. Okay, so infinite long means you see that a very long wire. Very long wire. See that whatever may be the length, we see that the electric field value remains same for the same value of R. Okay, for a very long length. So for a very long length, it is very easy to find the value of electric field only by using the Gauss law. So when you use other methods than this, it will become very complicated. Okay, for easy way of finding the electric field for infinite long wire, this is more preferable, which is given by Gauss law. So it becomes one of the applications of Gauss law. See, it depends only on value of R. For the same value of R, whatever may be the length, you get the same value of electric field. For different value of R, we will be getting the same value of electric field, whatever may be the length. Because this electric field does not depend on the value of L. Even though the charge depends on the value of lambda and L, the electric field is same for the whole infinite length, whatever may be the, so it only depends on the R. Okay, so this is the value of the electric field due to an infinitely long uniformly charged straight wire. Okay, thank you.